video we saw solidification of isomorphous alloys. So as I told, isomorphous alloys are those in which both the components, they are completely soluble to completely soluble in each other, both in solid as well as liquid phases. Today we'll see solidification of binary eutectic alloys. So binary eutectic alloys are formed with elements which are not completely mutually soluble in all proportions. So I told you previously that we'll see the difference. So as you can see from here, in case of isomorphous alloys, there is a single liquidous line above which everything is liquid, and there is a single solidus line below which everything is solid. But in case of a binary eutectic alloy, since the solubilities are limited, the phase diagram is divided by number of lines. There is a liquidous line AE above which it is completely liquid. Similarly E2F, another liquidous line above which it is completely liquid. But solubility of alpha phase, beta phases, these are different. We'll see what are alpha phase, what are beta phases, how the solubilities are different. So the example of an binary eutectic alloy is aluminium copper system, copper silver system, tin bismuth system. These are common examples of binary eutectic alloys. So the solidification behavior of alloys that exhibit limited solubility is graphically represented as eutectic phase diagram. So this is called as eutectic phase diagram. So if someone asks what is the purpose of eutectic phase diagram, so eutectic phase diagram, they tells us the solidification behavior of binary eutectic alloys. Binary eutectic alloys are those which exhibit limited solubility. So you can see for constructing binary eutectic diagram, we are taking example of copper and silver. So first we draw 2 points A and F. So point A corresponds to melting point of copper. So melting point of copper is 1085 degrees Celsius. So this is the melting point of copper. Point F corresponds to melting point of silver. So we draw, locate point F. From point A to point E, we draw a line, and from point F to point E, we draw another line. So AEF, this is the liquidous curve, not a line, it's sort of set of lines, so we call it as a curve. So AEF is the liquidous curve. I told you there are two phases, alpha phase and beta phase. Alpha phase is the solid solution which is rich in copper. So see, here copper is maximum, here silver is maximum. On the left hand side copper is maximum, on the right hand side silver is maximum. So naturally on the left hand side, whatever phase we are denoting, whatever phase is forming, that will be rich in copper. Similarly on the right hand side, whatever phase is forming, that will be rich in silver. So alpha phase means solid solution is rich in copper. See here copper is maximum and silver percentage is increasing from 0. So alpha phase is solid solution rich in copper and silver as the solute element, that is called as alpha phase. Similarly beta phase is the solid solution which is rich in silver and copper as it is having copper as the solute element. Another thing which you should remember is the concentration of silver is increasing from 0 to 100 from left to right. So here silver is 0, copper is maximum and it is increasing continuously. Similarly on the right hand edge, silver is maximum and copper is 0. So copper concentration will increase right to left. So the mushy region, alpha plus liquid and beta plus liquid, it is separated by a single phase region. So alpha plus liquid. Similarly beta plus liquid. And this is liquid and this is alpha plus beta. There is a reaction which takes place, we call it as eutectic reaction. We'll see it in detail. So these are the regions in the diagram. Also the line which separates the mushy zone from the liquid, we know it is called as liquidous region. The curve which separates the single phase with the mushy zone, we call it as solidus. But there is another region. See, this is the single phase region alpha, this is the single phase region beta, but they are in contact with the double phase region. Alpha plus beta is also there. This is also solid but two phase solid. So the line which connects the single phase region with the two phase region is called as solvus line. So this is a new thing which we have not seen previously. So liquidus we know, solidus we know. Solvus line is something which separates the single phase region with two phase region, and both are solids. Okay, moving on. Solubility of each phase, solubility in each of the phase is limited. So solubility of each of the phases is limited. So as can be seen from the diagram, at any temperature below BEG is called as the eutectic line or the eutectic isotherm. A limited concentration of silver will be dissolved in copper. So we can see at temperature around 780 degrees Celsius, the solubility of silver inside copper is maximum. So see the alpha phase region, the maximum solubility is obtained at 780 degrees Celsius, and the maximum solubility is 8 weight percentage. Means the alpha phase maximum silver for the alpha phase, it will be 8%. So alpha phase can have maximum of 8% of silver, and that maxima is obtained at 780 degrees Celsius. Similarly for the beta phase. So moving on, as I told, there are three curves. Till now we have only seen the liquidus curve and the solidus curve. That the liquidus curve separates the mushy zone from the liquid. Solidus curve separates the solid zone from the mushy zone. There is another zone here. The single phase solid is separated from two phase solid. So the line or the curve which separates the single phase solid from the two phase solid, that alpha separated from alpha plus beta, is called as the solvus line. Another thing is the line BEG. This is called as eutectic line or eutectic isotherm. So line BEG may also be considered as a solidus line. Whatever we have seen till now, this may not be apparent, but for this binary eutectic alloy system, we call the line BEG as a solidus line. Okay. So as I have told before also, few lectures back, that the effect of adding an alloying element to a pure metal is the melting point of that pure metal, it goes down. So you can see pure copper is having melting point of 1085, but if you keep on adding silver, it will continuously go down, and it will reach the minima at point E. Similarly, in case of silver, the melting point is around 900 something. So if you keep on adding it, adding the copper element, again it will go down. But the binary eutectic alloy system, both the system will have the minimum melting point at point E, which point E is called as the eutectic point, where the eutectic reaction takes place. So eutectic reaction is a typical type of phase transformation in which a single phase liquid phase gets converted into two phase of solid. So schematically you can say liquid upon cooling, it's getting converted into two phases alpha and beta. Conversely, two solid phases alpha and beta upon heating is getting converted into liquid. So for this particular case, we are saying liquid which is at 71.98%. If you drop a vertical line, you can find out this concentration of liquid is 71.9% of silver. So liquid at 71.98% of silver is getting converted into alpha. Concentration of alpha is 8 weight percentage of silver. So liquid 71.9 weight percentage of silver is getting converted into alpha at 8% plus beta at 91.2%. So this I have written here. Liquid upon 71.9% of silver upon cooling getting converted into alpha, which is 8% of silver, plus beta 91.2% of silver. Some other examples of binary eutectic system are lead tin system. So the diagram, the values will be different of course, but the general nature of the diagram, the scheme of the phase diagram is same. Next we will see the solidification characteristic of binary eutectic alloys. Look into the solidification characteristic of binary eutectic alloys. There are several regions inside the diagram which we will consider. So case 1 is compositions ranging between a pure component and the maximum solid solubility for that component at room temperature. So room temperature means very low temperature, and the composition ranging between pure components. So here we know the alpha is present, so alpha is the pure component, means single phase component is there, and maximum solubility at room temperature. So we are considering this portion. So again we are starting from the liquid region. So this is completely liquid, and when we cross the liquidus line, the alpha crystals will start forming. Then as we cross the solidus line, the alpha crystal, they will grow completely into, and then fill up the microstructure, and they will become alpha. So this we have seen previously. This solidification characteristic within this region is similar to the isomorphous alloys. We have a liquid plus solid phase, and then upon crossing the solidus line, it becomes completely solid, and then as you keep on decreasing the temperature, the solid size may increase. Okay. Second case is compositions ranging between the room temperature solubility limit and the maximum solubility at eutectic temperature. So this was the room temperature solubility limit at this location, and maximum solubility at eutectic temperature is this. So we are considering this portion. Inside this, what will happen? Again, we'll starting from liquid. If you cross the liquidus line, alpha crystals will start forming, because this is liquid, this is alpha plus liquid, this is alpha. So upon crossing liquidus, alpha crystals will form. Then upon crossing the solidus, alpha crystal will completely cover this. Now if you keep on decreasing the temperature, and as you cross this point, this star point, if you cross this line, we know this is called a solvus line. So as soon as the solvus line is crossed during solidification, beta phase will form in minute traces, because we know that beyond this solvus line, alpha phase cannot exist as a single phase, because if you cross the solvus line, you enter the two phase region. So alpha was already forming. If you cross the solvus line, beta phase will start forming, because this is alpha plus beta region, but these will be in traces only, and their size will increase marginally with continuation of cooling. As you decrease the temperature, the size will marginally increase. Now next is the most important reaction in this binary eutectic, which is called as eutectic reaction. So of course eutectic reaction will take place at the eutectic point. So there is the liquid which gets converted into two phases, alpha phase and beta phase, at the eutectic point. So here for the lead tin system, PBSN system, liquid is at 61.98%. You drop a vertical line from here, 61.98% of tin. So 0 to 100, tin is increasing, so 61.9% of tin. Upon cooling is becoming alpha, which is 18.3% of tin, plus beta, which is 97.8% of tin. So this is the eutectic reaction. The eutectic structure, it is sort of a lamellar structure. Means both the alpha phase and beta phases, they will exist in alternating layers. So alternating layers are formed because if an alternating layer is formed, local diffusion can take place, and the atoms which are diffusing, they don't have to move a longer distance. As we know, every system will try to use minimum of energy. So if they want to transport, they want to diffuse over a longer distance, then they have to spend a lot of energy. So they want to diffuse locally. If local diffusion is taking place, then such alternating layers will be formed. This is the SEM image of the same. Now next case is composition ranging from maximum solubility of alpha phases eutectic line till eutectic composition. So this is the maximum solubility of alpha phase at eutectic line, and this is the eutectic composition. So what will happen inside? So we'll start from the liquid. If you cross the liquidus line, alpha phase will start forming. Then till the eutectic point, alpha phase will grow in size, and as soon as you cross the eutectic line, the eutectic phases will form. So one major thing which is to be noted over here is the alpha phase which is forming before the eutectic point is called as pro-eutectic alpha. Before eutectic point, whatever alpha phase has formed, we call it as pro-eutectic, means before eutectic alpha. And after the eutectic line, both the alpha and beta phases will form, means eutectic structure will form, lamellar eutectic structure will form. So that will contain eutectic alpha, that will contain alpha phase and beta phase. So that alpha we call it as eutectic alpha, and that beta obviously just beta, because no prior beta is forming. So the alpha phase which is forming before eutectic line is called as pro-eutectic alpha, also called as primary alpha. And the alpha which is forming after the eutectic in lamellar form after the eutectic, we call it as eutectic alpha. So the next composition ranging from maximum solubility of beta phase to eutectic line, this you can draw yourself. I have not drawn here, means in this slide I have not drawn, not available in many books also, I could not find it anywhere. So you try to draw it and then tally with the answer. This is the answer, this is the solution. So there will be pro-eutectic beta and then the primary beta or the eutectic beta.